This first example is called a trig identity. Trig identities are when you have trig statements that are put inside equations, and your goal is to prove that those equations are true. Normally with trig identities, you're only allowed to work with one side, and it's usually better to pick the more confusing or the more complex side. In this question, I think we'll work with the left side for obvious reasons. The first step for most trig identities is to turn everything into sines and cosines. I have sine b over tangent b, so I think I'll replace tangent b with sine b over cosine b. So I'm going to work only with the left side. This is a complex fraction, so sometimes complex fractions are better written as the grade school version, sine b divided by sine b over cosine b. If I take and do the division by flipping the second fraction, I get sine b times cosine b over sine b. And now that I've got sine b times a fraction with sine b in the denominator, I can make them both into fractions, sine b over 1, and the sine b's canceled, and I'm left with cosine b or cos b. That's hilarious. Instead of proving identities that are trig equations, you are still going to be asked to simplify trigonometric expressions. The next example has two fractions added together, and I think the best way to add these two is to find a common denominator. Everything is already in terms of sine, so converting everything to sine and cosine isn't going to help because I've already started that way. So I'm going to take the first fraction, one over 1 minus sine theta, and I'm going to multiply it by the second denominator, 1 plus sine theta over 1 plus sine theta. If I do that, I have 1 plus sine theta in the top, and then 1 minus sine theta times 1 plus sine theta in the bottom. So I have my common denominator in the bottom. Now I need to repeat that same exact process for the second fraction. I have 1 over 1 plus sine theta. I need to multiply that by 1 minus sine theta. Doing that gives me 1 plus sine theta times 1 minus sine theta in the bottom, which is indeed my common denominator. So I can now add 1 times 1 minus sine theta to the top. 1 minus sine theta in the top. Now I can do some simplifying. The first thing I notice is that in the top I have 1 plus sine theta plus 1 minus sine theta. So this sine theta and that sine theta cancel out, and I'm left with 1 plus 1, which is 2. And in the bottom, when I multiply 1 minus sine theta times 1 plus sine theta, I wind up with 1 minus sine squared theta. 1 plus sine theta minus sine theta, and then negative sine squared theta produces that. I'm going to use that trig identity again that says sine squared theta plus cosine squared theta equals 1, because this denominator has 1 minus sine squared. If I were to bring the sine squared to the other side, I now know that 1 minus sine squared is the same thing as cosine squared. So my problem turns into 2 over cosine squared theta. The reciprocal of cosine is secant, so 2 cosine squared theta is the same thing as 2 secant squared theta. So I took the original two fractions, found a common denominator by using fancy versions of 1. This is nothing more than 1, and this is nothing more than 1. And once I found a common denominator, the top simplified pretty quickly. The bottom used sine squared plus cosine squared again, but in a different format to convert 1 minus sine squared into cosine squared. And then the last step is to get rid of the fraction by saying that cosine squared is the same thing as secant squared. And then the final example, same thing, two fractions. This first fraction has sine and cosine. The second fraction says 1 over tangent. I want to convert tangent into sine over cosine. But 1 over tangent is the same thing as cotangent. So the first thing I notice is that this is really cotangent t. So when I go to write 1 over sine t cosine t, minus cotangent t is the same thing as cosine t over sine t. So again, the strategy is get everything in terms of sines and cosines. Tangent, 1 over tangent is the same thing as cotangent. Cotangent is the same thing as cosine over sine. Now I need a common denominator. Both denominators have a sine, but I need a cosine in this second fraction, so I'm going to multiply by cosine t, cosine t. My common denominator is now sine t, cosine t. My numerator is 1 minus cosine squared t. And while I can't simplify anything in the bottom, this numerator should look familiar. It's almost identical to what happened in the previous problem. Sine squared t plus cosine squared t equals 1. If I take cosine squared t and move it to the other side, I know that sine squared t equals 1 minus cosine squared t. So 1 minus cosine squared t is the same thing as sine squared t. I have sine squared in the top and sine in the bottom. One sine in the bottom is going to cancel with one of the sines in the top, and I'm left with sine t over cosine t. But sine t over cosine t is the same thing as tangent t. So there's the final answer. So there was 6 examples of how to simplify algebraic expressions using trig. And again, a lot of the rules that you're going to see boil down to these identities. Sine squared plus cosine squared is 1, and this also turned into 2 new identities, which were sine squared theta equals 1 minus cosine squared theta, and then flip-flopping the sine and cosine. Cosine squared theta equals 1 minus sine squared theta. And then the other major hint for doing identities is turn everything into sines and cosines, and then you can simplify from there.